Hey everyone, this is Dr. Clyde Letzum again with the second part of the resistance in circuits and the body part 2. Alright, so what we're going to start off with in this part of the series is we're going to just refresh our memory as to voltages, currents, and resistances in circuits. And so the circuit that's on the screen right now is a series circuit. And so you can see here that we have a voltage source that's in series with 5 different resistors: resistor capital A, resistor lowercase a, resistor C, resistor lowercase v, resistor uppercase v. Okay, and if you recall, what we should expect is that whenever we have resistances in series, what we should have is different voltage drops across each of the resistors, as long as those resistors have different values. So in this case, then the voltage difference or voltage drop across A is going to be different to this one versus this one, and so forth. Okay, and so what we can say then is, if we wanted to find a total resistance, within this entire circuit, what we would do is we'd add up the resistor values from A, lowercase a, C, V, and uppercase V here to get our total resistance in this circuit. Also, if we wanted to find a total voltage, of course, we can look at what the supply voltage is supplying here, but if we want to also find a total voltage, if we knew what VA, V lowercase a, VC, V lowercase v, and V lowercase v are, then we would just simply add all of those up together, okay? And we would be able to figure out what our total voltage is. Now, I've been saying lowercase a and so forth, but do understand that these are subscripts, and these are here for a specific reason, and you'll see why in a minute. Okay, and before I go to the next slide, one thing I also want to point out is, if you recall, if these components were in parallel, then if we were trying to find a total resistance, we'd find the total resistance by doing 1 over R plus 1 over R2, meaning the components that are in parallel, you'll just go ahead and do the inverse of each of them, add them up together, and then take the inverse of the sum there. Okay? And one other thing I want to point out is, if we're trying to find a total current through this circuit here, then if we know what the total voltage is and we divide that total voltage by the total resistance, then we'd find the total current, meaning the current going through each of these components here. All right, on to the next slide. So on the next slide now, what we're doing is we're now moving over to the body, and we're going to look at series and parallel vessels within the body. So we're going to look at a very, very, very simple diagram here of the human cardiovascular system. And in the human cardiovascular system, we have a heart, of course, and then we have arteries, which then lead to arterioles. I think that's how you pronounce it. Then we go to capillaries, venules, and veins. Okay, and you can see here that we have this path here that's broken into 2 here, and then that path then is broken into 2, and this one is broken into 2 parts, and then they come back together at this point down here. Okay, and so this is kind of representative of like a combination type circuit, where we have the series going on here, then it becomes parallel, and then that part becomes parallel, and then this becomes parallel, but it's starting to combine again, and then we come back to a series point here, and then back to the heart. Okay, so now if we look at the same diagram, and now we say that this is one organ where the capillaries are inside that inside that organ, and then we have this organ here which has capillaries on the inside. Okay, and we're trying to figure out, or we have the flow of blood in this case going through these arteries and so forth into the capillaries, into the venules, veins, and so forth. We can, as you may figure, right, being that the diameter of these are going to be different, then you can figure that what we're going to have is we're going to have different pressures within all of these different vessels here. Okay, and if we happen to know what the different pressures are, as well as the amount of resistance that the blood will experience as it's going through them, then we can figure out what the amount of blood flow is through the entire system. And so on the side here, what I drew was a very simple diagram of what the blood vessels would look like, with the arteries, the arterioles, I don't know how to pronounce that, but that's okay, capillaries, venules, and so forth. You'll notice that they're different sizes, and then they start to get bigger again as they get to the venules and the veins. Okay, and so again, if you have different sizes, okay, and you have different resistances within, then we can figure out, we'll have different pressures, and we can figure out what the amount of blood flow is within the system. All right, so now let's make our system even simpler. We're just going to look at one single branch from the previous diagram, just one branch, okay? And therefore, we're just looking at one organ in there. If we want to figure out what the total resistance is within this entire branch here, as is shown on the screen, what we would want to do first is start with the capillaries, figure out what the resistance is within this area. And you all should know that from our previous studies that whenever you have resistances in parallel, you take 1 over that one of the resistor values plus 1 over the other resistance. We add those up together, and then we take the inverse of that, and we get the total resistance as it pertains to the resistors that were in parallel. So in this case here, we have these capillaries that are in parallel, okay, and we go ahead and we would find the total resistance within this area here, the capillaries, by doing this, okay. And so now we can figure out what the resistance as related to the organ branch is by now taking that RC that we found above and add it to RA, which is now the resistance as seen in this area here. And then we can add that also to the resistance as seen over here, and we'd get a resistance, total resistance, that's in this branch here. The reason why we added the 3 of those up together is because, of course, you all know when we have resistances in series, as we mentioned before, you just go ahead and add those up. Okay, so now if we're looking at the total resistance going through here, all right, then what would happen is we take the R0 from what we had here, RO, pardon me, from the resistance as related to the organ, and we'd add that to that of the vein and that of the artery, and that will give us our total resistance within the entire cardiovascular system, if this was all that was there, okay? And so if you all can recall, what happened is the pressure, like voltage, across any parallel component is going to be the same. And so since the pressure across any parallel component is going to be the same, then that means the pressure as seen across these capillaries in here are going to be the same. So we can, if we know, we can find the pressure across these. And if we have the pressure across this venule here and the arterioles here, then we can add those all up together, those 3 pressures, and figure out what the pressure is as it relates to this branch for the organ here. Okay, and so therefore then if we want to find the total pressure within this entire branch here as we go along here as shown on the screen, then that will be as shown here, where we take the delta P of lower or uppercase V plus delta P of O plus delta P of lower or uppercase A, and that'll give us our total pressure. Okay, and then since we have the total pressure, now we have the total resistance, we can actually use that in order to find the total amount of blood flow through the circuit, through this cardiovascular system, as shown here by taking delta P of T over delta, R of T, which will give us our Q of T. All right, so now if we had now the 2 organs in here instead of the 1 organ, then we would then go through, say we already know how to find, okay, the resistance as it relates to one of the organs. So we can use that information then and say, okay, we can also find the resistance as related to 2 organs by doing the inverse of the 2, because remember, these organs are in parallel. Okay, these organs are in parallel. And so if we do 1 over the resistance for organ 1 plus 1 over resistance for organ 2, and then we sum those up together and we take the inverse of that, we end up with the resistance as related to the 2 organs together. Okay, once we get that information, we can take that then and sum up that resistance with the resistance seen here in the artery and the resistance seen in the vein, and that will give us our total resistance in this cardiovascular system here as shown on the screen. All right. And so therefore then we can find the pressure. Okay. We can find the pressure of the organs. Okay. The pressure as it relates to the organs here. The pressure as related to the organs then would be equal to, remember, these two are in parallel, so that means they're going to have the same pressure across them. Okay, and so since we know that the pressure along here and the pressure along here, if we took the 2 of those together, then, all right, we will be able to find the pressure along this branch going along here and along this branch going along here. But remember, they're the same pressure, right? And so therefore then that's going to be equal to our delta P of O. So in other words, our pressure along here is equal to our delta P of O. Pressure along here is equal to delta P of O. But because they're in parallel, it's the same thing. Okay? And so therefore then that delta P of O plus the pressure in the artery over here plus the pressure in the vein over here is going to give us our total pressure. So again, this delta P of O up here is related to the pressure here plus pressure here plus pressure here. Okay? And remember, because these are in parallel with this one down here, we don't have to multiply by 2 or anything. It's exactly the same thing. All right? All right, so now given that information, we can now find the total amount of blood flow through these organs here by knowing the total pressure divided by the total resistance. And so that gives us then the total amount of blood that's flowing through this system. Okay? All right. And so that there completes our discussion then on resistance in the circuits and in the body. And so that helps you to at least understand that the same principles that govern the flow of electrons or current, let's go ahead and use current, in a circuit, an electrical circuit, are the same principles that are very much present when it comes to the cardiovascular system. And so you can clearly see then that what we're learning when it comes to circuits is very much viable when it comes to understanding the human circulatory system and understanding the pressures and the resistances within and the amount of blood flow also. So again, this is Dr. Clyde Ledsam, and this was discussion on resistance in circuits and the human body. And this was part 2 of the series. If you like what you saw, Harry, subscribe to my YouTube channel, or you can also check out information on my website. I thank you again for watching.